Thank you very much for introduction, and thank you for coming here to listen to my talk. And this talk is last, so obviously my main goal of this talk is not to overrun. Sorry, it is a joke, but anyway, so let's start. Today I'm talking about additivity questions and tensor powers of quantum channels. And maybe you have seen this topic, this kind of topics during this workshop already. But I plan to start with basics, so it may be boring, but people say that we should not stop running suddenly because it's not good for your heart. So let's start a bit slowly. So this is my talk today. So in the first part, we have set up and we introduce some basic knowledge and give some open problems first. And in the second part, I talk about the additivity problem, and maybe I mention some briefly some techniques in the proof. And in the last part, I talk about tensor powers of quantum channels. And maybe so in this talk, I'm mainly interested in randomly generated quantum channels, but I also mention some quantum channels, some theorem which does not depend on random construction. Anyway, shall we start? So, as you've seen before, quantum states and channels. So quantum state is a Hermitian operator, positive and trace 1. And in the second part, we define quantum channel. Quantum channel is a CPTP map, trace preserving. So this kind of construction. V and V are joint trace. This construction gives a CPT map, and if we choose a V to be isometry, it gives a trace preserving condition. Anyway, this is our quantum channel. So we have an embedding map V, which maps from C to L to C to K, tensor C to N, for example. And we call this K maybe output, and this C to N maybe environment. And as I mentioned later, briefly, we can switch these roles, output and environment, so that we can switch the roles. And so for some reason, for some problems. So sometimes this distinction between output space and environmental space may not be very important. Anyway, so we go on. So this is what I said just now. So let's try to take pure state as input, and this input will be embedded by this isometric V into larger space. And what would happen when input is just this kind of rank 1 projection? This V times this vector x will be decomposed by Schmidt decomposition like this way. And by taking a partial trace, so we we make product with a joint here, and when we take a partial trace, the cross product will disappear, and we get reduced density matrices, which is kind of proportional to R1 to RD. This corresponds to this Schmidt decomposition coefficient here. So in this sense, tracing out which space is not very important. Whichever we trace out, we don't have cross products anymore, and we get the same non-zero eigenvalue distributions. So in this way, if we only think of pure input states, output states, or environmental states is not very important. As I will mention later, I'm interested in entropy, and entropy is a concave function. So in this case, optimization. For optimization, we only need pure input state like this, because after spectral decomposition, eigenvalues are all positive. So naturally, we pick some pure input states to optimize some quantity like entropy. We'll see this problem soon. So in this slide, I'm going to introduce minimum output entropy. This is defined by this way. So here we have input row, and here we have channel. So this phi row is output of this channel phi, and we measure entropy like this. Entropy is defined this way, and we look for the minimum. And this is called minimum output entropy. And in this line, I made some small notes. Suppose we have a product of two quantum states. The entropy of this product is just sum of these two entropies. For people who are not familiar with this kind of calculation, I'm going to mention briefly. So we have eigenvalues for rho and sigma here, but with tensor product, eigenvalues are a multiplication of these two eigenvalues. But as you can see, we have log here for entropy definition. So this log makes this product into the sum. So this sum comes here. So anyway, so for product states like this, entropy is just the sum of two. But things are more complicated when we don't have simple product like this. So this relates to additivity problem of quantum channels. So this is also new important quantity, which is called Holm capacity. This is also called one-shot capacity. So here we have an ensemble of quantum states. So this P is probability distribution, and this sigma I are quantum states. And we look for optimum of these quantities. I'm not going into details for this quantity here today. If we regularize this quantity, we get the classical capacity of quantum channels. And I'm going to show the formula later. So anyway, so we have bound here. So this capacity, Holm capacity, is bounded by log d minus minimum output entropy. The reason is that, so for entropy, the maximum value is log d. Suppose we are working on dimension d, and here we have the average of input states. So suppose this average state is maximally mixed. We have kind of here the states proportional identity. Then we have maximal value here like log d. But on the other hand, we have minus here. So when we have minimum for entropy here, we get the max value as a whole. So then we replace this part by minimum output entropy to get the upper bound for this Holm capacity. Anyway, this Holm capacity has a nice relation between two. So here we only have inequality, but sometimes we have equality here. So this is true, for example, when we have this kind of covariance property. The idea is that, so we want to have maximally mixed state here. To do so, suppose we are given some pure state, then we rotate kind of equally to have the average as identity. Then we get this log d. But then suppose now we rotate it input, but then suppose if this rotation is commuting with these quantum channels, and then output is also mixed by these rotations u. So then we are done. So we pick. Suppose we pick some this sigma I to give this minimum value. Then we rotate. Then here we get maximally mixed state. Sorry, I made a small mistake here. But anyway, so then this rotation gives the maximally mixed state here. This is how it works here. Anyway, and then so this C is classical capacity of quantum channels. So this is given by regularization of Holm capacity. The reason why we have this kind of asymptotic expression is that, so when we think of capacity, in the first place, we want to know how efficiently we can transmit information. To do so, we are allowed to think of the infinite length of codes. And then we look for theoretical bound for transmitting information. This is why we have tensor n here. The reason why we have tensor here is that so we send signal each time, and suppose the noise is independent for to each other, then this kind of model can be written by tensor product of this phi tensor to n. Anyway, so then we take n as large as possible and regularize it, and then we think of the limit. Then this is then we get classical capacity of quantum channels. And sometimes this is true. We don't have to regularize. If this tensor product gives additivity outside of this capacity, Holberg capacity. For example, suppose this is sum of n chi of phi, then this n kills this n, and we get this formula. But this is not always true. This is called additivity violation. And as I mentioned, if we have phi and phi complement, and this is sometimes important, and also in general, this is not true. So this is true for minimum output entropy, but this equality is not true for Holberg capacity. The nice thing about this is, as for so let me go back a slide a bit. So here we sort of complementary channel. Suppose then we have k and n here. Suppose n is much larger than k, and which space we want to work on? Of course, we want to work on this space k, because what we are interested in are eigenvalues of matrices. But we have two spaces, and for these two spaces we have same non-zero eigenvalues. Then of course we would like to work on the smaller space, and in some problems we can fix this k to be finite and take n to infinite. Then we can keep track on the behavior of non-zero eigenvalues of outputs of quantum channels. Anyway, so this idea of complementary channel is important if we think of this inequality. So anyway, so in this field of quantum information, mainly we are of course interested in this quantity capacity, but this capacity seems to be difficult to investigate directly. So several persons like me are working on instead minimum output entropy to look for some clue for capacity of quantum channels. And then additivity violation. So what is additivity violation so far? So I'm going to show when additivity violation can happen in this slide. So suppose, so as I saw, quantum channel is written this way. So input here, and we have embedding to larger space, which is bipartite system, and we take a trace for just one space. And here we think the conjugate, complex conjugate of the channel, and this is defined by complex conjugation of this isometry here. And then if we take this V random, and then with high probability, we have this violation. As I mentioned, if we restrict ourselves to this simple tensor input, and then this problem is just sum of these two minimum output entropy. But as I mentioned before, we are not sure about the structure here. We may have more complicated input here. Then this minimum may gives a strictly smaller value than the sum of these minimum output entropies. Anyway, this is additive violation, and of course, this situation. The reason why I wrote this inequality is that so far proof is made for this setting, and there may be other setting, but we don't know yet. But it may be interesting to find other settings for additivity violation. And then, so Hastings proved additivity violation first. And what he did is so just he take phi random and phi bar random. So they are almost same apart from this complex conjugacy. And the difference could be log k over k. And the parameter k and n looks like this. So k is large, much larger than 1, and n is much larger than k. So here, this is a model he thinks. Actually, this is not written by isometry, but this also can be written by using isometry. But this is the model which Hastings used for the proof of additivity violation. And U is taken with Haar unitary IID, and Rj is a bit technical distribution for some reason. But anyway, this R is random, and the U is Haar random and IID. This is what he proved. And what we have then, so we have phi tensor fiber, and here we have phi and fiber, and the difference is suppose we have epsilon here. This is what is proven so far. And then we can take some, we can make some channel omega, and this omega we can make tensor for the same omega, and then we have violation like this. So just here we have the same value here, and then so we put them together, and then anyway, so if we take this omega to be phi, a direct product phi bar, and then we have this relation, and somehow we can make this omega more symmetric, and then we can form psi, and for this psi we have a variation like this, chi of psi tensor psi is larger than 2. I'm sorry, maybe this is equal. Sorry, this is equal to psi to chi psi plus epsilon. Sorry, this is equal. Anyway, then what is the capacity of quantum channels? As I said, so we can regularize this Holomov capacity to get capacity. But since the limit exists, just we take subsequence, just we take 2n. And then this inequality is obvious because we have 2n, but here we have 2, and n gets out. So then capacity, this Holomov capacity should be smaller than or equal to this quantity. So this inequality is obvious, as I said. So then, in fact, because this part can be written by this way, so we have this gap. So here we have capacity of psi, and here we have chi, Holomov capacity of psi, and we have this epsilon over 2 gap here. So, once additivity variation is shown, somehow we can make this original channel more symmetric to get some channel which, some channel for which capacity cannot be written by Holomov capacity. So this is so then we don't know about the one-shot capacity. I mean, simple formula for classical capacity of quantum channel. So this is, I believe, an important, very important question in this field. Anyway, so then, so let me show some example open problems first. Open problems first. First, we don't know about the additivity of classical capacity. Of course, we have additive variation of Holomov capacity, but to get this value, we have to regularize it, and we don't know what happens there. So we don't know. This is just like this. So we have two different quantum channels. Now we are allowed to use entanglement between these two quantum channels and send the information. And I don't know what is the capacity. Classically, we have additivity here, so we know that we have two channels, and even if we use them together, we can calculate capacity separately. But here we don't know. And what about the regularized minimum output entropy? This is also some question about the minimum output entropy, which is close to this problem. So instead of regularizing Holomov capacity, here we regularize minimum output entropy and see if additivity is true for this quantity. And actually, this limit exists for the same reason as for Holomov capacity. This comes from subadditivity, and we can prove within a paper, one-page proof. And then, anyway, so limit exists, and we want to know if the additivity is true or not. And another open problems. So we know that there exists some counterexample. So as I said, we take random quantum channels, and we can show that there exists some quantum channels which violate additivity. But finding concrete examples is a different problem. So far, we have some counterexample for p larger than 2, which is found by Grundga, Hordetsky, and Pankowski. And this is just we take a symmetric subspace of bipartite system. So as I mentioned, so quantum channel maps input space into embed this input space into a larger space, which is bipartite system. So in a sense, quantum channel can be identified as a subspace of a bipartite system. So here we have take two space, and then we fix some subspace to fix quantum channel. And Grundga, Hordetsky, Pankowski just chose this subspace to be symmetric subspace, and this quantum channel gives the additivity violation for p strictly larger than 2. So in this sense, we don't have counterexamples for p between 1 and 2, including 1 and 2. P equals 1 means entropy itself. Sorry, I wrote this question a bit general. I should have mentioned. So I talked about additivity problem in terms of von Neumann entropy, but here we use Renyi entropy. So Renyi entropy is written this way. So then if you take limit p to 1, we get entropy. So this is a general version of additivity problem. And for p larger than 2, there are examples found by these people, but we don't know any concrete examples for p between 1 and 2. And when p is 1, means p being 1 means that this SP is just a von Neumann entropy. Anyway, so we don't have counterexamples. This is also open problem. And so from now on, let's see what's going on very, very briefly for additivity violation proof here. So to show that minimum output entropy of tensor product of two channel has a smaller eigenvalue, we have to show that there is some input which gives some output which gives smaller entropy. So this is what's happening here. So we take some quantum channels and just input Bell states. So in this setting, this Bell state, this input Bell state gives output which has the largest eigenvalue larger than L over k times n. And to know how big it is, suppose suppose this L equals n. Suppose the input space and output space or environmental space has the same dimension. So then this L and n kills each other to get here 1 over k. But now we have tensor products, so the space of output space is k squared. So we are looking into matrices of k squared times k squared, but then we have some output state which has eigenvalue, which is larger than 1 over k. So this 1 over k is much larger than 1 over k squared. So somehow we can say that, so for Bell input states, we have an output which has rather small entropy. This is how we prove that we have a small entropy for tensor product of two channels. And this idea was first used by Heiden and Winter, actually Winter, and then other people also use the same technique to get the bound for phi tensor phi bar.
So here there is no relation between the k and the n, k being much smaller than
And also, so I was talking about randomly generated quantum channels, but this bound is true for any quantum channels. So we don't have any randomness here also. Thank you for your question. And then, so anyway, so let's get to the idea. So, I'm not going to show a proof, but let's see what's going on behind. To use by using this example, this is called quantum random unitary channels. The reason why we call this random unitary channel is that this rho is input, and we apply this rotation kind of randomly with probability 1 over k. Sometimes we have different coefficient here for each I, but here I chose the same weights.
So, but ui are fixed; they are not random.
Yes. So this is a bit confusing. So I think people call random unitary channels this way. So ui are fixed. Yes, ui are fixed, and then somehow we apply this rotation randomly. So people call this.
Sometimes they were called random external fields.
Thank you. Thank you very much for answer name. So actually I was looking for answer name. Anyway, so let's work on this example. And here we have psi tensor psi bar, and we have Bell input state here. And what's happening here is written here. So suppose we have U tensor U bar, and we have Bell state here, and then this Bell state is kind of fixed point. And maybe if you're familiar with representation theory, and if we have representation U over U actually, and then if we make tensor, and there is one-dimensional invariant subspace, and the other is the rest is the other, and so this corresponds to this one-dimensional invariant subspace, and then here so we make tensor. So by making this tensor, we have cross product like ui tensor uj bar, something like this. But when I and j have the same number, so here, so let's have a look at here. When I and j is same, here we have ui tensor ui bar, and then by this property, this b is fixed somehow. So then for each pair of ui and uj, we have this concentration here. So by this calculation, maybe some of you get convinced that for Bell input is very nice for this construction, tensor product of some quantum channel and the complex conjugate of this quantum channel. Anyway, so this is true for in general. Anyway, so then let's go to the next slide. So then, so now we know that tensor product of phi tensor phi bar has rather small entropy. So let's see that each quantum channel is a bit noisy, meaning that outputs of quantum states has rather large entropy. To see it, let's think about this picture again. So we have input here. As I mentioned, we only have to think about the pure input here, like A, and this A is embedded to larger space by V. Let's write this V times A like W. This is just a vector in bipartite system, and we take trace. And then by taking trace, somehow we just, in terms of matrices, we reorder elements of a vector to get matrix here. And the reason why I use W is that this is Wishart matrix, W, but this is a bit normalized. So here we have suppose we have random vector here. So here we have random vector in, yes, so suppose A is fixed and take this V random, and then we have random vector here, W, and taking partial trace, we get random matrix here, and this is Wishart matrix. But since we take this A to be to have a length 1, we have to normalize. So this normalization comes later. Anyway, so this is kind of Wishart matrix with some constraint, and then here as I wrote, so this is we star is kind of normalized Wishart matrix. And then we think about the eigenvalue distribution of this Wishart matrix, and this can be written this way. So here, this is a normalization. Eigenvalues should sum up to 1. And also, let's have a look. So important part is here. So this is just a square, so this is also important. Somehow, eigenvalues are repelling each other, and this is also interesting, but this part is more interesting today. And here we have n minus k here. So when n is much larger than k, somehow pi are close to each other. Somehow, if one of pi is close to 1 and the other close to 0 and so on, then this part gives this much smaller value. So, by this property, so when n is much larger than k, we have some kind of concentration of eigenvalues of this Wishart matrix. And so far, what we did is that so we fixed input, and we take random quantum channels, and we saw what's happening. And but to calculate minimum output entropy, actually we have to fix quantum channel first, and we have to go over all inputs of quantum channel to look for minimum output entropy. So in this picture, we change the problems. I change the order of problems. We fix input like this, some vector, and choose random quantum channels and see what's happening. And the calculation shows that so with when this parameter k, the n is much larger than k, we have kind of concentration of eigenvalues. And this problem was set by so of course this proof was kind of made by Hastings first, but this problem was set by Oberlin and Sharrak and Werner and so on. And what they think is that so we have this kind of construction. C to I hope I'm not wrong, and C to n to 1 plus 1 over p to Cn tensor to Cn. And then they use the Dobretsky theorem. By using Dobretsky theorem, somehow they changed the order of this problem and made a very elegant proof for additivity variation. What they showed is that actually in this setting, this minimum entropy, minimum Rayleigh entropy is actually close to this minimum entropy of this product channels, and of course as a corollary, and this is actually smaller than the sum of these numbers. Anyway, so and also they extended this technique to the original problem for entropy, additivity variation for entropy case here. Anyway, so this is what we do. And then I'm going to my research. So then a question is that, so now we know that additivity is not true for free tensor fiber. And our question is that what are good inputs for free tensor fiber? Is it a bare state? Is there any other beta state? To make sure this problem, we take random quantum channels in this picture, and we have input here. So here we have random quantum channels, phi, and we fixed input, and we saw what kind of behavior this matrix has. And of course, here we change the order of problems. So if we fixed input and we took random quantum channels, and we saw what's happening. And after calculation, so this is I think this was done. This has been done several years ago, and so then we have this kind of limiting eigenvalue distribution. And after calculation, we have this formula. So we have a big one eigenvalue like this, and smaller eigenvalues, many smaller eigenvalues like this. And here m is parameter written like this. And an, what is an? So we have kind of a regularization here, but anyway, what is an? n is kind of input. So as you remember, we have a vector here, and changing orders of elements in this vector, we get matrix, and then the trace of this matrix gives kind of important parameter here. And what is this? So suppose this A is maximally entangled like this, and we have some coefficient here. So corresponding matrix to this vector A is that that matrix is a diagonal matrix with entries alpha I. So suppose if we have Bell set here, alpha I are all 1. So the trace is dimension is L, so the trace should be L. But on the other hand, suppose we have phase here. Maybe we have a circle and we divide them into L parts, and maybe we get 0 for this trace. So even for maximally entangled states, we also have to care about this phase here. If we choose this phase to be 1, then we get trace here 1, and then we have a very large value here. So this is how it works. So after this calculation, we thought that probably Bell state is the best for input. Anyway, so then we also worked on phi tensor phi and phi tensor phi transpose, phi tensor phi star. And this transpose and star means that we make that isometry into transposed 1 or starred 1. But for this setting, we don't get anything good. And then naturally, so we make a lot of tensor here. So here we have phi tensor phi. So actually, we make tensor phi tensor phi var to some tensor R, and then we fixed input and we took random channels, and we looked for the best input for this setting. And our calculation showed that the best input is the tensor product of Bell state. Bell state can be any Bell state between these two groups. Maybe between here and here maybe, and here and here maybe, whatever. But anyway, so as long as we make tensor product of Bell states, and where each Bell state lives in phi and phi bar, then this gives the best input. And of course, here we change the order of problems. So this does not show exactly that for this kind of quantum channels, this Bell state is the best input. But changing the order of problems, after calculation, we show that Bell state, tensor product of Bell state is the best. So then, of course, then recently we worked on this problem. Okay, why not take phi and phi? And then in this example, I took even number of phi. Sorry, I should mention. So here we have phi. This phi is generated by orthogonal rotations. So as I mentioned, so this I should have mentioned that the isometry so far is kind of complex. So this can be generated by hard unitary matrices. But here, to generate random matrix, just we use orthogonal matrix. Take orthogonal matrix and truncate this orthogonal matrix and get some isometry, but which is made from real numbers. Then we made the same calculation, and we get the same result. So as long as we input tensor product of Bell states between two, where each Bell state lives in between two orthogonal channels, then this gives the best channels. So then, so our conjecture is here. So suppose we have orthogonal channels, phi tensor to R, then this may be equal to R times minimum output entropy of phi tensor to 2. And more weakly, maybe this is true after regularization, the additivity variation only happens for pairs here. This is the motivation of this research, because previously we have phi tensor phi bar, but this does not give any insight for regularized quantity. But if we take orthogonal channels, then phi bar is phi itself, so why not think of this? And maybe for orthogonal random channels, this may be true. So this is what we want, regularized quantity, and this regularized quantity maybe just at minimum output entropy of phi tensor to 2, but we are not sure. So let me explain. Let me introduce some other research which is related to tensor product of quantum channels. So this research was done by Montano. Maybe he may be here. I'm sorry if I'm wrong, but anyway. So this is isometry here, and we have a kind of projection here, and we have partial transpose here, and infinity norm. This gives a bound. So I wrote multiplicative bound because this tensor comes with this tensor here. So actually, this is kind of dealing with tensor product with inequality. And similar, inspired by this research, Nikita and I worked on this problem. So here this time we have two norm here, and this is bounded by partial transpose of Choi matrix, infinity norm here. This is multiplicative as well. And then anyway, so then Montano showed that we got additivity of quantum channels, and so yeah, this research is almost the same. And then, so this is the result with Gilad Gore, and this is not random, no random idea here. So we show that, I should mention, so I'm talking about, I'm sorry, two norm here, shut and p norm here. But if you think of linear entropy can be basically written by p norm. But because of log term, linear entropy, multiplicativity problem here change into additivity problem in terms of linear entropy. Anyway, sorry, suddenly I am using a shut and p norm here. Anyway, so with Gilad Gore, we worked on this problem. So phi tensor to R, and then we want to know maximum output to 2 norm of this quantum channel, and this is bounded by this quantity like this, and this gamma is written like this way, and here D is a kind of dynamical matrix of phi restricted to traceless Hermitian matrices. So basically, so quantum channel is a linear map. So we have identity, and we have other traceless matrices, which is orthogonal to this identity. And just we worked on this subspace, which is orthogonal to identity. And we just made a matrix, dynamical matrix here. And then this largest eigenvalue gives this quantity gamma. And actually, with using this gamma, we have this kind of bound for classical capacity. Here, log k. I think we have seen why we could have log k here. Log k plus log of gamma phi. And actually, this bound is tight for example, one Holm channel. One Holm channel gives this bound exactly. So this bound is not very bad. And so this is our research with Gilad Gore. And summary. So maybe additivity violation, maybe a special phenomena only for conjugate pairs. So as I mentioned, conjugate pairs phi tensor phi bar. And then purpose additivity violation typically does not hold for phi tensor n when phi is generated by unitary group. The result I introduced just a few slides before is about orthogonal quantum channels generated by orthogonal group. But maybe for unitary case, maybe we don't have any violation because I don't know, of course, there may be a violation, but based on some calculation made by us, we don't know. If it happens, it may not be generic property. It may be just an exceptional case. So here, this is unitary, but for orthogonal cases, there may be additive violation for pairs, but not anymore. This is our conjecture, and Yeah, otherwise, so this is conjunction. Otherwise, so somehow we have to show that this additivity survives. Somehow this additivity violation. For additivity violation to be true, somehow additivity violation must survive for tensor structures. So I mean, as make a higher tensor, the violation should be larger. To have a violation for regularized quantity. So this is the summary, and thank you very much for your patience.